Let's take a look at a second example problem for Module 7.2. So in this problem here, we're given a direct derivation of state space model mechanical translating. So in this case here, we have a cart, mass M here, spring here with K2, spring here at K1 there. We can see we have this force here, Fa of t, displacement x in this direction, displacement z from this point here, and we have our damper over here at B, and we say our input is our Fa and our output is this z over here. They asked us to derive a state space model for this system shown right here. So now that we've read through the problem, understand what they give us in the statement and the diagram, the next thing we want to do is create our setup page. So we're looking for a direct derivation here, state space model. So we're given this given diagram right here. Again, there's our mass right here on the cart. There's our spring constant K2, our K1 here, our distance of the cart here, our x, and our z over here. And we have this force input right over here, Fa of t. And we can see over here we have our B for the damper there. So key equations we're going to utilize in this problem here is F equals ma from Newton's second law, and energy of a spring 1/2 kx squared. So those are the key equations that we'll be drawing from as we solve this problem. So the first thing we want to do, I redraw out my diagram up top here, because I want to create my free body diagram, and from that develop my equations of motion. So the first thing I really want to do with this, once I have my diagram redrawn up here, is to choose a coordinate system. So I'm going to show positive x going to the right, positive y going up here in a standard Cartesian coordinate system. So now I want to look at the mass itself. So I'm going to look at this cart right here and treat this as the block for my free body diagram here. And I ask myself what's acting on it. Well, I can see I have the force over here from the spring at K1. I have the force over here now from K2, so that'll be K2 times that distance x there. This one, the displacement over here, is going to be our z minus our x term right there. We have this external force, our Fa of t, as our input force right there, and we have our mx double dot here as well. So from this here, we can take a look at that and say, okay, what is the summation of my forces? Well, going in the positive x direction here, I have this Fat from this right here. So there's that force positive right there. I have a positive spring force from this spring right here and this right here. So that's my K1 times Z minus X. I'm going to have a negative Kx from this spring force right there. So I write that in as my negative Kx. I'm going to have a negative Mx double dot right there. And this is all going to be equal to 0. So that's the summation of my forces in my X direction. So from this here, I can rearrange now and I can solve for my Fat, my input right there. So I can solve that there. I say the Fat is equal to, when I rearrange a little bit, mx double dot plus k2x minus my k1 times z minus x. I can distribute this k1 through there, and I end up with this relationship that my Fa of t is equal to my mx double dot plus k2x minus k1z plus k1x. So now I can take a look and my system 2 here on the right side over here. I can take a look at the z direction over here and realize, okay, from this object over here, I'm going to call this again my positive x to the right, positive y up. So moving this direction would be my negative x direction here. So over here I can see I have this spring force there, and I have this b times z dot acting there for system 2. So I can redraw out my summation of forces now for system 2. So the summation of my force in the x direction is equal to now a negative from this guy here, k times z minus x minus b times z dot is equal to 0. So I rearrange this a little bit here, distribute that k1. I say bz dot plus my k1z minus k1x is equal to 0. So we know there's 3 energy storage elements. So there should be 3 state equations. So 3 storage elements are my spring 1, spring 2, and my mass, or k1, k2, and m. So next we can choose our state variables here. So we have our x variable here. This is the energy in the spring K2, which is given as 1/2 kx squared. For our x dot, or our velocity term here, we have the velocity at x, which is the energy of the mass here, which is 1/2 mv squared, where again v is our x dot. And for the energy in spring K1, we have 1/2 k z minus x quantity squared. So we can pick z as our state variable. So now we have our state variables shown up top here. So I have my Q1 is my X, my Q2 is my X dot, and my Q3 is my Z. So now we can get equations for the derivatives of this, so we can use the equations of motion from the free body diagram here. So that Q1, Q dot 1 is equal to X dot is equal to Q2, Q dot 2 is equal to X double dot, which is equal to 1 over m times FA minus, now in this case here, K1x minus K2x plus K1z, where this is from our equation of motion down here. And we can solve that for x, and we solve it for x, this is what we get for this relationship here. So that's what we use to plug back in for our x double dot over here for this relationship right there. So once we plug that in, we can redistribute this here. Now we say our Q3 dot is equal to our Z dot. So this right here, now we have our K1 over B times our X minus Z right here, where again we have our X and our Z given up here as our Q1 and our Q3 there. So now the question is, where does this K1 over B come from? So we come down here to our system number 2. We had this general equation here, our BZ dot plus K1Z minus K1X. We can solve this, rearrange and solve for our Z dot. So our Z dot is equal to negative K1 here plus K1X over B. So we can do this. Z dot is equal to 1 over B times our K1 times Z plus X, or Z dot is equal to K1 over B times X minus Z. So that right there is what we plug back in up into here to replace for our Z. So that's where we get this relationship from, is from our Z dot that we solved from our system number 2 from our equations of motion. So now I can rewrite the things that I've solved for here for our state variables, and we have that our Q1 dot is equal to X1, which is equal to Q2. Our Q2 dot is equal to X double dot is equal to, again, this over here, 1 over m times FA K1X minus K2X plus K1Z. Over here, again, we have our Q1, Q2, Q3 there. And we also now have our Q3 dot is equal to Z dot, plus now this relationship that we just solved for there, K1 over B from our system number 2 equations of motion, is equal to K1 over B when we plug in for our Q's, Q1 and Q3 there. So now, again, we recall when we plug those in, this is our Q1, Q2, and Q3. Plug that in, simplify it down. Next thing we want to do is get this in matrix form. So we have this general expression here that our Q dot is equal to AQ plus BU. So what is our A? Our A, we come up with this 3 by 3 matrix here, 0, 1, 0, K1 plus K2 over M, 0, K1 over M. Then down here in the last row, we have K1 over B, 0, negative K1 over B. And then our B matrix here, column vector is 0, 1 over M, and 0. If we multiply this out, we can double check that everything comes out correctly. But this is our A and our B in matrix form here. So then we go back. Again, we have this relationship here. Our Q1 dot is equal to Q2. Our Q2 dot is equal to this relationship here with now our Q1, 2, or Q1 3s in there replacing it. And our Q3 dot is equal to K1 over B times our Q1 minus K1 over B times Q3 there. So now we have this Q dot is equal to our AQ plus BU relationship here. So now I can plug in, here is my Q dot vector right here. Here is my A matrix. Here is my Q vector there. Here is my B, and here is my U there. So we can see how we come up with all of these guys here directly from this here. So this is all in matrix form. Then we have our second, our C and our D over here from our Y expression. Y is equal to C times Q plus our DU, where now our C and D are given by these guys here, where our D is 0.